All right, so we will talk about gravitational waves. We started talking about this last time, and I just want, the reason I'm talking about this is I think this is one of the greatest experiments done in science in recent times. Okay. Now, here's the deal. So, if you want to emit electromagnetic waves, like the waves that you use, your cell phones rely on electromagnetic waves. Radios, when you listen to the radio, it's electromagnetic waves that you're receiving. Okay, so a station is sending electromagnetic waves which carry energy, which drives current in your radios. Okay, so to make electromagnetic waves, what you have to do is you got to grab hold of a charged particle and make it accelerate. Yeah. So give it an acceleration. And here's how you can do it. Grab hold of a charged particle and make it oscillate like that, and it'll emit electromagnetic waves in this direction. Okay? And this is done on a dipole antenna. So here's two pieces of metal, and essentially you'll learn next semester this acts like a capacitor, and this will emit electromagnetic waves. Now, if you want to emit gravitational waves, you have to do the same thing. Instead of a charged particle, what you need is just a mass. Take a mass and make it accelerate, and you'll emit gravitational waves. The only problem is the following. To emit gravitational waves that are detectable by us, just because gravity is a very weak force, you have to make a very massive object accelerate. So, for instance, you can take this piece of chalk and make it accelerate. This is emitting gravitational waves, except that there's no way in heck you'll detect this. You can grab hold of Earth and make it oscillate, which the sun is doing. Okay? When the Earth is going around the sun, it is accelerating. Remember, a uniform circular motion, while it's accelerating, is two simple harmonic motions. The Earth is accelerating and emitting gravitational waves. Again, those are too weak to detect it. Okay. So if you take a very massive object and make it oscillate, make it accelerate, it'll emit gravitational waves. All right. So we detected gravitational waves for the first time in September 2015. That's almost 10 years ago. Okay. Here's a black hole, a massive object that is being accelerated. It's going around another black hole. So to make this black hole accelerate, you recruit another heavy black hole. Okay. So they're going around each other. Okay. And we detected the gravitational waves emitted by these guys. Okay. These guys were 1.3 billion light years away. Okay. So it took 1.3 billion years for that signal to reach us. Okay. Now here's what happened. So this was 1.3 billion years ago. Those guys had been revolving, going around each other for a long time. And as they lose energy, they get closer and closer. Okay. And we only saw them for the last 200 milliseconds. Okay. So they were winding towards each other. Okay. And just before they merged, we saw this signal that lasted about 200 milliseconds. All right. Why did we see this only now? Then the last 200 milliseconds and not all that signal. Why do you think that was so? Yeah. Hey guys, it is the greatest science story, and you're talking on your phone. So why do you think that happened? this was a very weak signal. It was strong enough only at that for the last 200 milliseconds. Okay, so that's what we detected. Okay. All right.
Is it because of the change in mass that occurred when they merged?
Well, then they're accelerating faster and faster. They're going faster and faster. The acceleration is greater and greater, and the intensity is related to the acceleration. Okay. So a parallel of this is I have an electron in my hand. I'm jiggling it, and it's emitting electromagnetic waves. It's emitting more intense waves. Okay. All right. So this is absolutely amazing. Okay. The more you think about it, the more it'll boggle your mind. Okay. So when the gravitational wave passes you, what happens? Okay. So here's what happens. So here, let's say this was a set of marbles or any object. Okay. So and we arrange them in a circle, and if no gravitational wave passes, they'll be in a circle like that. And when a gravitational wave passes, here's what happens. This circle, this space gets distorted like that. So this circular space got distorted. It got stretched that way, and then got stretched this way, and then back like that. Okay? So it would stretch that way, go back to a circle, then compress that way, and then go back to a circle. All right, well, how much did it stretch? Okay. So here's how much it stretched. If the diameter of this thing was 1 meter, it stretched to 1 meter plus 10 to the minus 21 meters. One meter stretched to 10 to the minus 21 meters in that last 200 milliseconds when the signal was strongest. When all those millions of years, when the black hole was going around it, how much was it stretching? Less, much less. And there was no hope of detecting that. We barely detected this. Even that, to put that in perspective, I mean, so you measured a stretch of 10 to the minus 21 meters per meter. Okay? Okay, to put this distance in perspective, you guys remember what is the size of an atom? 10 to the minus 10 meters. So this is the billionth of the size of an atom. The size of a nucleus is 10 minus 15 meters. The size of a proton is roughly 10 minus 18 meters. All right. So again, I mean, how the heck do you detect this distance? Okay. So, well, 1 meter stretches that. So one of the things we did was, well, what we'll do is we'll take something that is 10 kilometers long, roughly. That's 10 to the minus 4 meters. So 1 meter is stretching that much. 10 to the minus 4 meters. 10 to the 4 meters will stretch 10 to the 4 times that minus 17 meters. Okay, so 10 kilometers is from here to State Road 40. So something that long will stretch the width of an atom. And we're going to detect that. Okay, you guys following this? Okay. Yep.
So, was there technically, since like you gave the example with the marbles that they stretched, they elongated, and then they went back.
Yeah, no, so if you had arranged a circle of marbles like that, the space like this stretched in this direction, then it goes back to a circle. Okay, so.
So was there technically no change? Or
Technically, no, what do you mean?
after it went back into a circle, did it Was there no change?
Yeah, okay. Think of a wave going on a lake. Once the wave passes, the lake will go back flat. Yeah. All right, so again, you guys understand? So we're still going to detect this distance, roughly the size of a proton. How are you going to do that is the question. All right, so here is something called an interferometer. So this is the instrument we use to detect this. Okay. So here is a laser beam. What this does is it's a beam splitter, and like the name suggests, it splits the beam into two parts. Okay, and this is roughly, it's actually 4 kilometers. So just to keep it simple, we'll say 10 kilometers. Okay. So this one beam goes and reflects back up there and comes back here. So, and this beam goes and reflects back there and comes back here. So you have two beams that have traveled roughly 20 kilometers. Yep. Now, so when the beams come back, one beam comes with a crest like that. Let's say this beam comes with a crest like that, and this beam comes with a trough like that. Okay. And so that's how you set it up, and they exactly cancel each other, and you have no light. When a gravitational wave passes by, if this space stretches like this, now this beam has traveled an extra distance. When this beam travels an extra distance, now there is a mismatch. And there is no exact cancellation. So that's how we're going to detect it. Okay? When this stretches, this has traveled a longer distance than this, and again there's a mismatch like that. Okay, the mismatch, this is highly exaggerated. The mismatch is ever so slight because this distance was 10 to the minus 17 meters. That's how much they've moved. Very small distance. But that's how they're going to, okay? So this was large enough only in the last 200 milliseconds. Okay? Had the event happened closer, the signal would have been brighter. Okay? Do you guys understand that? All right, so, and here is the signal. Okay, so you were measuring this light intensity in the photo detector. Okay, so here was brightness. When did this cancellation happen? No brightness happened when it's gone back to the circle. Again, the beams cancel exactly. Okay? And you see, just before the merger, the signal is getting brighter and brighter because the intensity is getting brighter because this distance is slightly increasing. Okay. All right, again, this is two black holes going around each other. This guy, one of them is a 29 solar mass, the other one is a 35 solar mass object. These black holes were traveling at 60% the speed of light. Extremely violent event. To put it in perspective, after I read the slides, anyway, you can do an easy calculation. The electron that goes around the hydrogen atom, that is traveling at 0.01 the speed of light, 1% the speed of light. Here is a massive object traveling at half the speed of light, 60%. In this, and again, so I'll spew out numbers. It's really very hard to comprehend. Okay. So here's the sun, our sun. In 10 billion years, it'll lose about 2% of its mass in 10 billion years. This one event emitted 3 solar masses in 100 milliseconds or 200 milliseconds, essentially. Okay? Imagine the power emitted, and we could barely see it. That's because gravity is such a big force and it affects things very little. Okay. So the amount of power emitted was, if you could see gravitational waves, if you could see it with your eye, it was as bright as the light emitted by the rest of the universe. That's how bright it was. All right. So we detected this. Okay. So here's the next question. Again, this is absolutely amazing, the small distance we detected. All right. Well, here's this lab happens to be in Louisiana. Okay. Now, if a truck goes by, that'll shake that distance, and you'll see some light. You might see a signal. So how do we know if it was a gravitational wave or a truck driving by? You guys understand the point? Okay. So,
Super sensitive.
what's that?
It's super sensitive, so.
Yeah, it is super sensitive, and that's why if a truck goes by, it can detect the shaking of the ground. So that's a valid question. So what they have to do is, they spend billions of dollars building this lab. You build an identical lab over there. And if you get the same signal in both the labs, then it wasn't a truck, and it was a gravitational wave. All right, so that's how they would verify all of this. Again, like I said, this is, I'll say it. It's the greatest experiment that we've ever done. Yeah.